All right. Yeah, thank you all for having me today. Like Addie said, I'll talk to you about some PSI efforts that are underway within the Science Mission Directorate. There'll be a little overlap with things that Noah said and also some crossover into STMV, but that's okay because we like doing cross-directorate work. And just a disclaimer, this is like the first thing I'm doing fresh off maternity leave, so if I'm a little scattered, we'll blame that. Go ahead and go to the next slide. So probably most folks on the call are already aware, but I wanted to throw in a slide just to give a brief overview of PSI, at least in terms of what we're thinking about and why it's important. So we know that the Plume-Surface interactions on the moon blow away dust and rocks at high velocities and potentially spread these particles across the entire surface of the moon. And you can see some frames here from Apollo 15 descent video images of the dust blowing right during the landing sequence. And so the approach I'm going to take today is looking at how these blowing particles can potentially confound surface science. You did just hear Noah say that for Apollo, our science wasn't greatly impacted, but we still need to think about this for different types of science measurements. We also know that PSI can insert dust into lunar orbit, potentially impact both hardware on the surface as well as in orbit. So far, we haven't seen PSI actually create a crater beneath the spacecraft, but we're obviously going back to the moon with much bigger spacecraft, so it's something to keep in mind. And I won't hit on the rest because I have a lot of other things I want to get to. Next slide. So why is PSI important to the Science Mission Directorate? Just a couple of reasons. This is not all-inclusive, but primarily we are looking at how we can preserve quote-unquote pristine lunar science. When I say this, I think particularly of things like sampling activities. It can be during a crewed EVA, or if you have an in situ robotic mission that's taking, some kind of sample or measurement directly beneath the lander. You need to know what was disturbed, how it was disturbed, etc., before you can really claim that you have a pristine, quote unquote, sample. We also are looking to protect not only our spacecraft, but any deployed scientific payloads and other nearby assets, both during descent and ascent. And then we also need to just understand how our scientific measurements from our payloads are affected or not as a result of spacecraft interactions with the surface. So how did things like regolith properties change? How does the lunar surface and atmosphere affected by PSI? And then also looking at volatiles and PSRs, permanently shadowed regions. Next slide. So a couple of environmental impacts of PSI, just to kind of elaborate on looking at how things have changed on the surface as we're taking measurements. We know that there are morphological changes. We get things like erosion in clods. We see evidence of surface smoothing. You can see in the Apollo image there. There's evidence for changes in grain size based on analyses done of LRO images of the landing sites. We don't have the right kind of Apollo sampling data to kind of confirm this, but that's something we can look forward to for upcoming Artemis missions. Again, surface smoothing and grain size changes can occur up to hundreds of meters away from the spacecraft if you have something that's on the scale of an Apollo lander. And again, scaling up to things like HLS, this will be much greater. And then finally, there's potential for injection of volatiles into the local environment, some of which can migrate to cold traps. There's been a lot of great papers recently on this topic. I think there's a presentation by Parvati later also discussing this. This is particularly important looking forward to Artemis. Things like Starship landings could deliver large amounts of water to PSRs that could make it far more difficult for us to uniquely determine the source for any intrinsic surface water that may be present there. So bottom line, understanding these environmental impacts is critical for interpreting our scientific measurements. Okay, next slide. I'm not going to spend a lot of time on this one because I want to get to kind of some of the activities we have going on. But again, we are obviously very interested in PSI impacts to our deployed assets. From SMD, this would be particularly our deployed payloads. We just selected our first ones for Artemis 3. So we're spending a lot of time discussing and thinking about what the impacts to these will be, especially during ascent of HLS. Like, will it be physically moved, blown away, reoriented? Will they be covered in dust? Will they be pitted, sandblasted? Do we need to protect them? Can we protect them? Can we get them far enough away, et And there's evidence of this. Again, Noah alluded to work done by Phil and Chris Emmer on looking at Surveyor 3 pieces that were returned and some sandblasting that occurred as a result of the Apollo 12 landing that was only less than 200 meters away. All right, next slide. All right, so I'm getting a little deeper into SMD's involvement in PSI activities. Again, some of this is going to overlap with other directorates. So we are flying payloads on our commercial lunar payload services program deliveries, so CLIPS. So we're funding several payloads that will take PSI-focused measurements and or characterize lunar environment in an effort to understand the effects of PSI. Noah just had a great presentation on how LRO has been contributing to understanding PSI, not only for our historic landings, so Apollo, Luna, and Surveyor, but recent and upcoming missions, so Shanga and Artemis, for example. And then finally, our Artemis activities, we're actively working with other mission directorates to ensure that PSI measurements are being obtained both in advance of and during crewed Artemis missions. And then our deployed payloads and mobile assets, so things like the Lunar Terrain Vehicle, are going to contribute direct knowledge to the effects of spacecraft landings and the ascent on the lunar surface. And I think Sean mentioned in the beginning, SMD has been involved in the PSI working group, and we did participate in the recent PSI 10. So again, we're having a lot of conversations with a lot of different people on this topic and how we can get the appropriate measurements and observations. Next slide. All right, so I'm going to go through a few slides here that outline our SMD-funded CLIPS payloads. These are either payloads that are taking direct PSI measurements, or they're taking some kind of measurement of the surface or the local environment that can help us understand the effects of PSI. I'm not going to spend a lot of time on each one because several of these have their own dedicated presentations coming up, and they can probably do a much better job than I can of telling you about all of the measurements they're taking. And with each of these, you'll see the delivery listed. So TO is task order, supposed to be the task order that they're flying on, as well as I tried as much as I could to put the landing site in if it's known. So first, and these are in no particular order. Again, baby brain, I decided not to worry about getting these in the right order, so just bear with me. So the first payload is Regolith Adherence Characterization Payload, or RAC, flying on Task Order 19D that's launching here in just a couple of months to Mare Crisium. So this is actually an experiment that's going to determine how lunar regolith sticks to a range of materials that are exposed to the lunar environment. And a lot of the results of this are going to inform how we can protect spacecraft, spacesuits, and habitats from abrasion. So this will be more relevant to protecting assets that are on the surface when there's a lander that lands nearby. You've heard SCALPs come up several times. And again, this is actually an STMD funded payload, but I put it on here because SMD is funding these deliveries, and I wanted to make sure that it was highlighted. So this payload will capture video and still image data during descent. Our SCALPS 1.1 version is going to also collect topography data to determine the total erosion during PSI as well as the rate of change. So this will be really great payload flying here. We've got it flying on Task Order 2IM, TO2IM, as well as 19D coming up again. Next slide, please. All right, so Heimdall you'll also hear from later. Heimdall is flying to the Gruithuisen domes on CP21. And so Heimdall will be imaging the landing plume to characterize how much and how far the regolith particles travel. This is one of several investigations that Heimdall will be conducting. It will also characterize lunar regolith after landing and map the landing site for geologic context. So we'll be getting descent imaging data as well as imaging directly under the lander to help us understand the effects of PSI. Lunar VICE, the Lunar Vulcan Imaging Spectroscopy Explorer. I'm not sure if this one's being highlighted during the next 2 days, but this is a joint lander rover suite, also flying on the same delivery as Heimdall. So we're going to get kind of double PSI measurements here, which will be fantastic. So part of Lunar VICE's measurements, so kind of one of its primary goals is to determine the composition and physical properties of rocks and regolith at the Gruithuisen domes. But they also have a lander camera suite that has context and descent cameras to image PSI during descent as well as characterize regolith properties. Next slide. We have SEAL, the Surface Exosphere Alterations by Landers payload flying to the South Polar region on CP22. And this one's going to investigate the chemical responses of lunar regolith to thermal, physical, and chemical disturbances generated during landing. They'll also look at the lunar exosphere and characterize that. So we'll get some good data here on changes that occur directly as a result of a spacecraft landing. And then finally, I think this is the last one I have highlighted here, is MSOLO, the mass spectrometer. Oh, sorry, I do have one more slide. Anyway, the mass spectrometer observing lunar operations. This one will be measuring composition as well as day-night changes of both natural and delivered gases near the lander. So this could potentially include any gases that are a result of PSI. This one's flying on Prime 1, coming up here also in a few months. Next slide, please. So we also have PITMIS, the Peregrine Ion Trap Mass Spectrometer. So this one has actually already flown. Unfortunately, if you've followed CLIPS, you'll know that it did not quite make it to the surface of the moon, which is a bummer, but had it landed and been able to get its primary observations, it would have characterized the lunar exosphere both after descent and landing and throughout the lunar day to help us better understand the movement of volatile species. And then Lunar Vertex is another lander rover suite that will be flying to Reiner Gamma. And they'll be looking at the origin of lunar magnetic fields and their relation to surface swirl features. But they're also going to assess the photometric character of the lunar surface. And this will help us to understand why the effects of PSI, which we refer to often as blast zones, why these blast zones have optical properties that are different than undisturbed regolith. So we'll get some good ground truth data for our orbital observations from LRO with Lunar Vertex. All right, next slide. And so this is an image of our recent CLIPS Intuitive Machines landing, TO2IM, which attempted to land near the South Pole, kind of ended up tipping over on its side. But here you can see we got an image of PSI. That you can also see here where the leg broke during landing. But again, just to highlight the importance of getting these measurements, you can see there are some fairly decent sized particles being blown by this relatively small lander. So something we really need to keep in mind as we return to the surface of the moon. Again, looking forward to getting more of these observations with our CLIPS payloads. Next slide. I'm not going to spend a lot of time on this since Noah just gave a whole talk on LRO. But like you said, LRO did kind of pave the way for a new series of observations and data on PSI by providing this really great orbital imagery. We have over 15 years now of images. We have images of the historic sites as well as now before and after images of recent sites, to allow us to directly make observations of the effects of rocket exhaust on the surface. And these photometric methods we've used have allowed us to predict how the surface has changed physically, as well as for determining the spatial extent, so how far out these effects go for different scales of landings. Next slide. All right, and finally, just to kind of talk a little bit about our Artemis PSI activities. Again, I mentioned our deployed instruments. While we've only selected the first 3, we do have an active solicitation on the streets now for Artemis 4, and we'll continue to do this for future Artemis missions. And we'll be selecting payloads that can take important environmental measurements that contribute to our understanding of both the superficial and atmospheric effects of PSI. Like I mentioned, we're currently investigating what the safe distances are for deployment and other methods for protecting payloads that want to survive after HLS leaves the surface. We have a lunar terrain vehicle that will have the capability to carry crew and payloads outside of the blast zone, allowing for kind of true pristine measurements and sampling. LTV may also be able to image descent and or ascent of HLS and help contribute to more observations of PSI. And then we're also working with other mission directorates to ensure that the HLS vehicles, again, both before and during crewed missions, have appropriate imagers and sensors to measure PSI. Again, this is really helpful for us to understand impacts to our science and to our payloads. And I think that's all that I have. Go ahead and hit next slide, make sure I'm not forgetting something. Yep, okay, great. So again, I'm very thankful for this workshop and for everyone's interest. And if I have time, I'll take a question. If not, I'll hit them up in the chat or the IO tool. So thank you.